Hello, everybody. Yeah, my name is Tobias. I'm one of the co-founders of Toposens. And yeah, I want to explain to you how Toposens uses sound and AI to come up with a very low-cost 3D perception system to understand our environment better. And this introduction by Jasper was pretty good because when thinking about explaining what we're doing, I came up with these clips. I hope the sound is on. So maybe you know the movie The Dark Knight. Yeah. So The Dark Knight, in this scene, Batman, because he's very good at.
Took my sonar concept and applied it to every phone in the city. With half the city feeding you sonar, you can image all of Gotham.
So what he was saying, so what did Batman do? So he implemented a 3D sonar system inside every smartphone, and through everybody has a smartphone in his pocket, and through emitting sound, he could see all the surroundings. What this comes up to then in a scene, the quality isn't that good, but still gives you an idea what's happening.
Okay, you got POV on Alpha. I'm Leon Beta.
So he's able to see everything.
The SWAT team on the stairwell. Another SWAT team on the roof.
Lights clear.
So you can see the waves being emitted.
Barbara, calm down. He has the kid.
So why am I showing this? So it's a nice introduction, but the most important thing is, okay, if you've been seeing this movie, okay, this is totally unrealistic, this is Batman, this can never happen. We have developed this. Yeah? So that's the trick. So what I'm holding here in my hand is maybe not the smartphone technology, so we're not at that level yet, but in general, we have exactly created what you can see here in the movie. So we have invented the bat sensor. So for the first time ever, we can understand our surroundings like bats can perceive their environment through ultrasound. Oh, now it's jumping a bit. So here on the left, you can see our initial sensor we're just releasing to market in about 2 months. And our technology is mainly based on software, algorithms, and artificial intelligence. So because what is basically happening, maybe you know how bats perceive their environment, and that is very similar to what our system is doing. We're sending out high-frequency sound, we're receiving signals, we process the sound, and then we get 3D data. So every one of our systems generates a 3-dimensional point cloud, as I think 2 talks ago we have seen you can do with a camera or a LiDAR system. The awesome thing about our technology is that we don't care about lighting conditions at all. It is a very robust system. Next big topic is it's the cheapest 3D sensing technology worldwide, because we only need a very small processing chip to do all this 3D processing. That's due to the special software and technology we worked on now for over 8 years in total. What is another factor? This system is not the long-range system. It's very good at short-distance sensing, so up to 5 meters. Since we're using sound, you cannot look for 100 meters, but you can sense up to 5 meters, which gives you a lot of applications in the automation space. And then, another important topic, especially on the lower right-hand side, is our system only generates a super small amount of data. So when we let the system run for about an hour, we are in an area of 3 to 5 megabyte in data, in 3D data our system is generating. So now think of what artificial intelligence algorithms can do with this data. You can do AI processing on the edge because the data amount is so small, you don't have to upload it anywhere. So where are we going with this technology? Automation is happening everywhere. I think that is pretty clear. We have already talked about it now and seen some topics. If you talk about the robotic space, you can look at consumer robots, you can talk about industrial robots, and as well as in the automotive space. So passenger cars, autonomous driving, that's why I was asking a question a bit earlier, but also commercial vehicles are automated. Every autonomous system needs to perceive its surroundings, so 3D sensors enable these cars to drive and move and interact with the surroundings autonomously. Up to now, the dominant systems which have been doing this task were mainly 3D cameras and 3D LiDAR systems. So both of them optical based, so sending out light or receiving light and then processing it. And this is exactly what we are changing now. Our system is using sound, so a totally different approach. Why is this important? So why do we need this kind of technology out there in the market? So these are some of the cases where short distance sensing is failing. So the existing systems don't work properly. Why is this the case? The environmental conditions are problematic. The close distance 3D data isn't good. The systems are just too expensive to equip your object, your autonomous system with a sensor. So several things lead to these kind of failures, and they cause deaths, injuries, a lot of physical damages. So close distance sensing for autonomous technologies is just really a gap that hasn't been solved perfectly. Especially prices also from the very expensive optical systems is keeping all these technologies from using good close distance 3D sensing. And sure, that is exactly what we are solving with our 3D ultrasound sensing system. So maybe here I want to show you, give you an idea how is our system implemented into a driving vehicle. So for maybe you know your park distance control sensors, which you already have in the car. So they give you one-dimensional ultrasound, so only the distance. With our processing, we're able to generate 3D data. So we send out sound, we get the sound reflections back, we process the data, and we get three-dimensional point clouds, as you get with other systems. So if a car is driving, equipped with our sensors, all the sensors fire and send out sound, we get the reflections, and we generate a 3D point cloud of the surroundings. This is still a simulation, but in a second you can see like real life data. So this is what it looks like when we are driving out in the street. So this is close distance up to 5 meters 3D data. It's a bit difficult to interpret for the human eye. The data is color coded, so on the lower level you have blue, then you go into green, orange, and red. What we are able to see, what is very difficult for other systems, is, for example, curbs. So small things on the ground, which is especially important for autonomous driving systems in the close distance maneuvering and parking space. Maybe you have already tested one of the autonomous parking functionalities in one of the more luxury type cars. Many of them don't work, only work in 50%, say, no, there's an error, I cannot park. That is mainly due to bad sensor data. And that is exactly what we are providing. Maybe to jump one step into the robotic space, I talked about vacuum cleaner robots, or I have shown them on another image. So this is an idea of how our system is perceiving the close distance surroundings in your home. So you can see the 3D point clouds of the sofa, compared to other systems, we are very good at detecting glass, for example. So that is also another thing that is difficult with optical systems. So how does the system actually work? So I'm talking about 3D sensors, but what's behind this thing here I'm holding here in my hand? So initially, I talked about the bad echolocation. Our system is working very similar to it. So I have a small speaker here. We send out ultrasound, so pulses of sound. All the surrounding objects reflect the sound, so in typical echo. We have microphones in here, and those microphones listen to the reflections. And then inside our processor, all the processing is happening. So we calculate the time of flight. So how long does it take for the sound to travel from our system to the object and back? And then our algorithms do all the 3D processing that you get 3D data out of this small system. So in the end, on the hardware side, our system is very simple. You need our chip, we call it the Sound Vision 1. You need 3 microphones. We just started a cooperation with Infineon because they also see the relevance. Okay, now we can not only listen to our surroundings with microphones, we can start seeing our surroundings. And the major component company for transducers, for senders. So those are the major components. 1 transducer, 3 microphones, and a chip. Sure, a bit of PCB and housing and so on, but that's it. And you have a 3D sensor. The magic is happening inside the Sound Vision 1. So now what are the software blocks? Where is lower and higher artificial intelligence happening inside our system? So up to now, most of the data processing is a lower level of artificial intelligence because we are looking at the data that our system is receiving and finding different things. So one thing is the echolocation. So once we process the sound data, we need to find where are the echoes, because you have a noise level, so there's lots of noise in such an audio signal. You need to what is a real echo? What is a real echo I'm seeing here that relates to an object? Otherwise, you have many false positives. The next point is the timing analysis. from this audio signal, you need to super precisely find out what the timing is. Yeah, so you need very good analytics and processing in the billionth of a second area, so in the nanosecond area, that we can process 3D data. And then, sure, there's all the 3D processing that we generate this 3D point cloud. And now this is the next level where it becomes really interesting. So the 3D data analysis. Once we generate all this 3D data, what can we do with it? I mean, that's where how we start understanding our surroundings since we process the 3D data we are seeing. And I want to quickly explain to you what has to happen to get highly reliable deep learning machine vision data out of this, to understand your surroundings. That is a topic we're currently working on, so we don't have the perfect deep learning neural net already installed. And these are 4 very important prerequisites which we found out over the last 1 to 2 years, which you have to have before you can really train a proper neural net. So one thing is you need very reliable data. So every sensor needs to give you the same data. Yeah, if you have a very high discrepancy between the different sensor systems, it becomes very difficult. You need very precise data, yeah? So you need to be in the very low centimeter, if not even millimeter area per point you're receiving. So you need to have a very high performance. Then you need a high density. You have maybe seen the video and have seen, okay, we have a rather sparse point cloud. That is more difficult to train a neural net on that than if you have a very dense point cloud, which is easier than to do with optical systems. And then for sure, if you have met all the other 3 topics, you need large data sets. Generating more and more data, the easier it becomes to train your net. So what are the steps for us we're working on and have ahead of us to get to real intelligence, what we think about when you think about artificial intelligence typically. So we are like directly in the middle between step 1 and 2 right now. So we have reliable sensor data now, and we are able to detect patterns because objects give us similar patterns. Then on the next level, we want to start understanding different objects in a static environment. You place your object there, you scan it, I don't know, 1,000 times, 100 times, and replace it with a similar object with maybe a bit of a different shape, but in a static environment. That's like the next level task. Now, when you think about all our vehicles where we want to apply these sensors, the next level is dynamic objects. Yeah, so you have to move from static objects once you recognize them and have a very high probability of hitting the right targets with your neural net. Then you can move on to dynamic, which makes it a lot more difficult because it's moving, the data can look different, and so on, so brings another level of complexity. Once you have solved that, then you can go to the maximum level you need for autonomous driving, which is the real intelligence that you can start making predictions around your environment. So if you see a human and recognize it as a human, can label it as a human, what is that person about to do? Yeah, is this person moving at a quick speed, slow speed? Is the person sitting somewhere? Is he standing? And the same with cars and your other surroundings. So that's like the maximum level we can go to, and we are still in the middle of this. This system, so we don't want to keep everything to ourselves. We are working on this, but this is also like an open shout to everybody who is interested in this kind of topic. We are selling these sensors without all of these steps because we want to spread it out and we want to democratize 3D sensing. So everybody who is here or is interested in building up neural nets based on our data sets, then please happy to talk afterwards. No, that was one too quick. So here you can just see how many companies are interested in this technology and the capabilities, what you can do with it. So it's pretty broad. We have many customers on our list already, many of them interested. So there's a lot of things for us to do to service all these inquiries. We are partnering with NVIDIA, for example, for autonomous driving and neural nets working on that. I talked about Murata and Infineon already, and then some other partners. The founders, we are 3 founders. My co-founders are the guys working on the technology, which invented the sensing system. Myself, I'm the business guy in the round, and represent the technology and talk to customers. And last but not least, what is our roadmap for this year? So we're standing here today at Rise of AI. In about 2 months, in July, we're launching our first commercial product. So not a test kit anymore, but like an openly available product, which is mainly targeted at robotics, companies, but can also be used in different areas. Then next level, what we're currently working on is an autonomous driving development kit. So with several sensors, which all aggregate the data that you can come up with something similar you have seen in the video. And we're currently on our roadmap to start working on the commercialized automotive sensor. And you talk about a sample as like the first step, and that will be done by end of the year. On top of that, we're currently starting to raise our Series A round. The company has been financed by some Silicon Valley investors and German investors up to now, with a total funding amount of around $2 million. So if there are any investors in the room, happy to follow up afterwards again. And now I'm happy to take your questions. Thanks.
All right, then we have the first question. Thank you, Tobias.
So the question is, what does it actually have to do with machine learning? I mean, okay, the applications you can build on top of it, obviously, but inside, it doesn't look for me like any machine learning algorithm needed. You can do this with classical signal processing, so on, right?
So as I said, we're not in the, we haven't trained any big neural nets right now. Yeah, so we're just starting off with that. I think what is more what we want to bring over, that we are building the cheapest 3D sensing technology where you can train, which you can implement in almost every topic, in smart building, into consumer electronics, into robots, into cars, where you can start training your nets on. We are just starting with this, I think the main point is that we are delivering the basis now, that we have reliable data, but we have to do all these steps with a very new technology, and I think just as you heard from Konux, you need very good data. So about, I think, 6 to 9 months ago, we started really intensively working on this and came to the conclusion, oh, wow, the data we thought was easy to handle with neural nets is not that easy to handle. So you have to take many prerequisites, so it's 80–90% before you can really then train your net. So rather see it as an enabling technology for artificial intelligence at this point, and we're moving on to the next level. So we're not saying we are the AI company right now.
Thanks a lot.
Great. Any other question from the audience? Cool. There's one.
Thank you. Very interesting product. The question is, do you see your product, where do you see your product in the line of autonomous driving? Because a sonar sensor, you said it yourself, is good for 5 meters, but if I'm driving, I travel 5 meters in half a second. So if the sensor classifies a person, the person's dead.
Very short answer. If we talk about full autonomous driving, our data is being added onto the full sensor stack combined with LiDAR sensors, camera sensors, and so on. That's why I said near-field sensing. And you currently don't have a proper technology which is able to cover that close distance. And the close distance becomes important if you drive slower. But every autonomous car has to start somewhere, it has to stop somewhere, and there are maneuvering situations, and in all these situations you need full 360-degree coverage also of the close distance surroundings. So it's a complementary technology to also the other technologies and not the single one. Yes, please. Behind you is the mic.
Hey, so famously, Tesla is not using the LiDAR technology, right? They're using cameras for the self-driving, but they're also using ultrasonic sensors, or something they call ultrasonic sensors.
Yes.
So is this something similar to what you are doing, or?
Yeah, very, very interesting question. Tesla uses 12 1D ultrasound sensors. Let's say, so due to NDA reasons, I cannot talk about the details. But let's say a company like Tesla is extremely interested in the level of data we can provide, because that's what they need to properly have their autonomous driving features fully rolled out. And this is one of the missing important pieces right now. That's,
One more question and then break.
Yeah, thanks for the talk. Are you planning to expand like the frequency bands of that device to do like real sound detection, also passive sound detection?
Sure. So what is our system is pretty, let's say, hardware agnostic. So it's really very software focused. So we can use any kind of transducer, so any kind of speaker, any kind of microphone, and any type of frequency. Sure, you have to adjust the hardware a little, but in the back, it's mainly adjusting the software. So for sure, you can also use it, yeah, maybe for hearing the sirens of an ambulance in the city, or like kids playing around. So for these kinds of safety features and a lot of other topics, I think are possible. Yeah.
And also from the images I saw, they didn't look for humans. They didn't look like they have much information,
Yes.
other than that there is something. Is it enough to do like some sort of image recognition, image classification, object classification with that data?
Yeah, that's exactly the part where it becomes tricky, which is a tricky part for us. What we found out that it's not, we cannot just use typical approaches of optical data, put it onto our data, and it works. But we have to like train new types of neural nets on that, and have to see what are the specific data points or the specific patterns we can see inside of that data. And the longer you start looking at an object, the more data we get, the more shapes we get, the more points we get, the denser the point cloud becomes. But that is something, yeah, to be executed on and see where we're going. Yeah.
Okay.